Good day and welcome to yet another of our series of lectures in inorganic chemistry. Today we want to look at isomerism in coordination compounds. By definition, we can say that isomers are compounds that have the same molecular formulae. By the same molecular formulae, we mean the same type and the same number of atoms, but structurally connected in a different way. The atoms are the same and the same in number, but they are linked to each other in different ways. Remember, when we discuss coordination chemistry, we talk of spatial or geometric shape. Spatial, the way the atoms are dispersed in space. So when we talk isomerism, we mean when the atoms are exactly the same and the same in number, but the interconnectivity within the molecule is different. With the difference in interconnectivity, such compounds will show differential properties. Further on, to make it easier for us to understand isomerism, we have divided isomerism into two major subclasses. These are structural isomerism and stereoisomerism, as you can see in the chart below. The scheme below to my left shows structural isomers, which constitute coordination isomers, hydrate isomers, ionization isomers, ligand isomers, and linkage isomers among the few. And you also have stereoisomers made up of two subclasses, geometrical isomers and optical isomers. We're going to start our discussion looking at structural. Structural isomers we refer to coordination isomers are those isomers where both the representative of the metal center. Remember, when you talk of coordination compound, you are referring to that molecule that has a metal center and a ligand. But when you talk of coordination isomers, you are looking at two different coordination compounds, whereby one serves as a metal center and the other serves as a ligand. As you can see in hexaamine cobalt 3 hexacyano-chromate 3, you will see that here there are 6 units of cyanide attached to chromium and 6 units of ammonia attached to cobalt. But in the interchange, chromium has moved into the ammonia sphere, while cobalt has moved into the cobalt sphere. You can see that the cyanide is now housing cobalt, while ammonia is now housing chromium. These two are known as coordination isomer. Hexaamine cobalt 3 hexacyanochromate 3 is a coordination isomer of hexaamine chromium 3 hexacyanocobaltate 3. Another typical example of coordination isomer is where you have 5 ammonia attached to chromium within the coordination hemisphere, where you also have chlorine. The chloride has the bromide outside, but in the second isomer, you see that the bromine has moved into the coordination isomer. The bromine has moved into the coordination isomer as shown by the parenthesis, while the chloride has moved out to the ionization sphere. Remember, coordination compounds have two valencies, the primary and the secondary valency. This type that has exchange in anions can also be referred to as ionization isomer, given the fact that when bromine moves in and chlorine moves out, there's exchange of ionization within the coordination hemisphere and the ionization hemisphere, which is there is a change between the primary and the secondary valency. To hydrate isomer. Hydrate isomer is easy to understand. Easy to understand because you're talking of hydrate, water. So hydrate isomers refer to that situation where water molecule or molecules are exchanged within the coordination isomer, the inner coordination sphere and the outer. As you can see, hexaquocobalt 3 chloride has 6 units of water within the coordination sphere and 3 units of chlorine in the outer, in the ionization sphere. But now that 2 units of water has moved out of the coordination sphere, the primary valency sphere, and 2 units of chlorine has moved in, you refer to that as hydrate isomer. There's exchange of position of water. Further, to now look at stereoisomers. You may do good to look at other of the structural isomers as highlighted. Stereoisomers refer to such complexes having the same molecular formulae but different spatial orientation of the ligand within the coordination sphere. We've talked about the spatial dispersion. There are two types of stereoisomers, the geometrical isomer and the optical isomer. We start our discussion with the geometrical isomer. These are those isomers are mostly commonly seen with the square, planar, and octahedral complexes. As you can see below, you have, we may not want to give it a name for now, but look at that. The green ligands are arranged on the same right-hand side of the blue unit against the navy blue carrying three different white atoms arranging to the left. Because these two are on opposite side to each other but arranged together, we refer to it as same side isomer. And by same side, we mean cis isomer, cis, same side. The two greens to the right and the two navy blues to the left. And that tells you of a cis isomer of a geometrical isomer. In the same vein, you also have the other isomer whereby it is still a square planar molecule, but the ligands are arranged in opposite direction. The two greens are to the left and to the right, and the two blue carrying three atoms are arranged on top and below. And at that point, you call them trans isomer of a type of geometrical isomer. We move on to another to show example with the 6 bonded or octahedral. In this, we have represented in such a way that you see the polygon, you see the rectangle lying in, you have to view it from a three-dimensional view. And by three-dimensional view, you see that the x, y, x, x, y, y are arranged such that this one lies in the axial. View it from the X, Y, Z coordination, and you see that the two grains are lying as though they are the X. If you see XX, you view it that this one is lying to the top and this one is lying to the corner of the rectangle, while the other four Ys are lying to the side. And you call that the cis isomer of an octahedral. Same applies as was in the case in square planar. The two greens lying here are lying one above and one below, while the two navy blues are lying within the apices of the rectangle, and you refer to that as the trans. There is yet another which you refer to as the facial and meridional isomer. By facial, take a look at the axis x, x, x lying here in the skeletal view. And you see that the x are lying to the axial and to the apices of the rectangle, and you call that the facial isomer of octahedral. Further on, you have the meridional. You will still take a look, you see they are lying y over x. As you can see, y is lying above, x is lying above y, while x and x are lying opposite to the diagonal. You can see y and y to the diagonal of the rectangle, x and x to the diagonal of the rectangle, while the other y and x are lying opposite as in three-dimensional view. I will refer to that as meridional isomers. We to see what we refer to as optical isomerism. By optical isomerism, we refer molecules are said to exhibit optical isomerism when the one of the structure is the mirror image of the other. Remember, when you are using your right hand to eat, you see yourself in the mirror as if you are eating with your left hand. If you point your right hand in front of a mirror, it appears as if it is your left hand. If you join your two palms, the two palms of your hands together, you realize that the left palm is exactly as though it is the right palm. As you can see in the structure here, there's a mirror lying in between the deep blue object, which now shows a reflection at the light blue object. So the deep blue object is the object, while the light blue is the image. Therefore, the light blue is a mirror image of the navy blue. So when an object shows a mirror image of the other, when a molecule represents the mirror image of the other, he has exhibited one property of optical isomerism. Further on, the molecule must not be superimposable on the other. For this, the only way you will understand, apart from the image we have shown here, is put the back of your right hand over the front of your left hand. You see that the thumb are pointing to the two different directions of your body. They can never merge as if when you put them two front of your palms. So the left palm and the right palm, when put over in reverse order, that's the back palm over the right palm, displays non-superimposability. You can see from the structure we have given you here, the blue and the pink structure. If you bring them over to the left, the first object, you see that the pink object or the red object, as your color would tell you, is almost covering up the blue object. While to the right, you see that the blue object pulled over the red object cannot be able to cover the other. So to the right, it is not superimposable. Therefore, it is optically active. But to the left object, it is superimposable. Therefore, it is not optically active. Therefore, the left-hand side image is not optically active, while the right-hand side image is optically active. The third, which is not what we demonstrate here, this one has to do with apparatus. The third principle that will tell you that a molecule is active is when you put it in a polarized light. You find out that the two molecules will reflect or rotate the plane of the polarized light in opposite direction. To the left and to the right, the two cannot turn or rotate the plane of polarized light in the same direction. So when a compound displays any of these three or these three properties, we say this molecule or this compound is an optically stereoisomer active compound. Another example we want to show is the structure showing red for oxygen, navy blue for nitrogen, zinc in the middle, sulfur and chlorine. You see that the left image is the exact replica, but showing the other one to the far left. So at this point, we say it is chemically active or optically active. Then at this point, we will request of you to please visit our PDF file in, as we are going to post the link for you. We have the PDF file in Google Drive, and we're going to post the drive connection, the link for you to get this in the PDF format as we end this video. Thank you for listening, and God bless.